Good too.
So here's where we saw these are the stochastic differential equations. And what this says is the difference in U is going to be some function of the current x, u, and y. And if that's all we had, if this is all we had, then we would have a differential equation. This would say the update is given by, the change is determined by x, u, and y, and what the specific rule for determining the change is can be, up for discussion. But we're describing the change through a rule that depends on the current information. What makes it a stochastic differential equation is that it has this additional omega sub u term, um, where omega sub u is a random variable. So we're not always going to get exactly the same change based on the current information, but rather we will get a rule that is applied and then some initial stochastic noise is added on. So this will not generate a single trajectory like an ordinary differential equation would. Rather, it's going to generate a bunch of different possible trajectories, and each of these different possible trajectories will have a probability associated with it. And that's going to be dependent on what the original deterministic update rule F sub u is, and what the original stochastic process omega sub u is. So this is, incredibly general. And if we plugged in specific Fs and specific omegas, then we might see specific results. But this is an example of something that we talked about a little bit last week, which is a stochastic differential equation. And the point here, I don't have I've never taught a class on these. I've seen them a little bit in my work on cryptocurrency consulting, financial modeling. But mainly, I know this from seeing other people do it. And so this is something I'm actively working to try to understand better. So one thing that I find is helpful is to see, is there a specific example of this that I can come up with? So what would it look like if I came up with, like, what is a stochastic process? Do I know an example of a stochastic process? Do I know, so one of the things you can do here is actually done in the book. You can start removing information and seeing what pieces you actually have. Because for me, as someone with my brain, um, I get overwhelmed by information when it occurs in like large amorphous chunks. And so what I have to try to do is give it a structure. And I liked how the book did this with the expected free energy. This has 5 parts, right? But then you start looking at, what if I drop this part? What if I drop this part? What if I drop these 2 parts? And maybe I understand this part where I just dropped 2. I don't have a name for it, but it's like you cover up part of the information and you see if you can grasp that single piece. So I do have a large principle for this I've developed, which is called the 2 confusion principle, or the stepladder principle. And it says, try to go one step at a time. Maybe we'll call it the single uncertainty principle, or stepladder principle. So when you're trying to climb these things, resist the temptation to like jump 4 steps at once. Go one step at a time. find one thing you are uncertain about and fill in that one step. So I developed this principle when I was trying to teach machine learning, or when I was teaching machine learning. And I was explaining, or we were discussing different models. Like we're discussing a random forest, we're discussing a boosted tree, whatever. And then we're looking at data. We're trying to look at data on stock prices. Well, there's a problem here because if we don't know much about stock prices and we don't know much about random forests, we have almost no hope of understanding anything because we don't have a starting point. We don't have a concrete way of like how if I understand one, I can use it to understand the other. So this is a principle I've been trying to use. I understand differential equations, don't understand stochastic differential equations. So I'm trying to leverage whatever I do understand about the deterministic case to advance to that next step of my understanding. And a lot of times just stopping and saying, okay, what am I confused about? What of this do I not understand? Um, there's something psychological that happens here. Because if we don't have any contact with the familiar at all, our brains tend to go into modes of uncertainty, anxiety, and then it's easy when we get in this uncertain place for the uncertainties to begin to spiral. That's something I don't know if y'all have experienced. It's not pleasant, but like when you're just imagining things, you can start to imagine basically anything. Whereas if you make contact with some aspect of concrete reality, then suddenly you have a grounding point. So are there any things that we're seeing where maybe we could find like the next step of what we would want to fill in, or where we're confident up to a certain point? And it's okay, one of the things for me at least, it's okay. You have no idea how deep these things could go. None of us do. So we got a few weeks ago, we were looking at the different base of the logarithms and how that could change the answer we got. If we're trying to come to consensus on what an answer should be, but we're using different bases of logarithms, that's a place where we could need to fill something in. The key though, all of this that I'm trying to do is not just, okay, let's review these symbolic manipulations, or let's prove this theorem, although those things might be important. But there's also this highly metacognitive strategic aspect of how do we decide what we're going to think about and how we're going to think about it to leverage. And I have all these things I've developed, this toolkit for getting to mathematical understanding from wherever we're starting. And I'm trying to share those tools as well as hopefully using them to gain some insight. So I'm gonna be quiet for a few minutes and see if y'all have any thoughts on what I've said or any questions as to specific things you'd like to dive into.
Euler's number and when you would use the natural logarithm versus other logarithms
Hmm.
and
Yeah.
why.
Yeah. Why would you use a particular base for a particular logarithm? Um, Euler's, I mean, it's called the natural logarithm. It's kind of a cop out, but it's the rate at which things tend to grow naturally. Um, it's also useful because e to the x is its own derivative. And so sometimes that cleans things up where you don't need an extra constant hanging around. Um, so let me talk about why would you use log base 2? Why would you want to use 2 for the logarithmic base? So computer scientists are going to use log base 2 because they're working with switches, right? And things are either on or off. And so it makes sense in terms of the kind of, also they're often working with trees to model that. So log base 2 comes from things tending to grow like binary trees. And sort of like when you get to the next level, there's twice as much. So using log base 2 kind of helps you know what level you are on in a binary growth process, roughly speaking. So why would you use log base 10? What's the advantage or what intuition comes from using? Why would we use log base 10? We have 10 fingers. And so the metric system is based on, uh, so are you working at the order, are we looking at kilometers or are we looking at centimeters or millimeters? Log base 10 does a very good job of telling us immediately kind of what scale we're on, where scale is a metric system type scale or number of digits in the number. Here we're looking at number of bits. What's the advantage of log base E? Um, well, not sure I've ever thought about that before. I thought way more about the other two types of logarithms. And even though as a mathematician, I use log base E all the time, I'm not sure why. That's my go-to. It has these nice properties. There's some nice properties about e to the x and e as a number, some limiting things. Um, like if you are doing continuous growth, continuous compounding, e kind of naturally pops out. But as to what intuition it gives in terms of I don't have intuition for it the same way I do for what log base 2 and log base 10 tell me. So maybe that's an interesting thing we could put in our sack to think about for the future of how intuitively does log base E help us? And if anybody has thoughts on that, I'm happy to consider them. I'll put that in the. It's usually just important that once we pick a base, we're consistent with it, or that we are clear on what base we picked. But I'm sure there is some intuition here. Another technique that's useful here, or has been useful to me at least, in terms of keeping things approachable and concrete, just like active inference with these mathematical things. A lot of times there's a high road and a low road, and or maybe we can think of it as abstract and concrete. So with all of these equations, maybe some people have sufficient experience that they see it and it immediately means something to them. And there's really no need for them to do else. I don't do anything else. I can't be inside other people's brains and know how they're thinking. I do know that a difference between mathematical thinking and other types of thinking, in my opinion, is that there's really less discrepancy between what is said and what is represented. And what I mean by that is in like political speech, you can talk about all these very abstract concepts like equality or freedom or whatever. You can come up with, very elaborate and nice sounding phrases, but they lack any real referent. So when we come to, what does freedom actually mean? What does freedom look like? Then it becomes its own huge discussion that is ultimately unresolvable. And math doesn't work that way. When you say something mathematically, it's intended to have a very precise meaning and to be unambiguous and uncontroversial as to what the term is representing. So one thing that has been helpful to me in looking at these things is to look for running examples or for things I can plug into the theory to sort of see how it would work. So one thing with these different discussions of variational free energy and expected free energy is you can just think about a common situation where you would have two different probability distributions and then calculate and see what would the difference be, or what would these quantities be for these two different situations that you could consider. So as we use it over and over again, it can become more concrete to us. So a couple of weeks ago, something we started to do and did not arrive at, but we could go back to it, is looking at this for two different coins. If you think that if you think that you have a 50-50 coin, but you actually have a biased coin, how much, what do these things look like? What does Kolek-Lieber divergence look like? And that was the one we were actually looking at. So if we're approximating a biased coin with a fair coin, how do these numbers change as the bias gets more and more away from 50-50, whereas the distribution gets further and further from equal on each outcome? So I think it would be worth going back to that if you have any interest in doing it. Hello, we have a newcomer. How are you? Cool. So I'll be back in just a moment and we can go through the different um, we can go through Kullback-Leibler divergence for two coins, and then maybe we could look at other models and see what that looks like. Okay, so let's define our two distributions here. We're going to have two different coins. And let's have P be the fair one. And let's have P be the biased one. And let's have Q be the fair one. Sticker. So Q is going to be the biased coin. And let's take this. And so P is distribution where heads has a probability of 50-50 and tails has a probability of 50-50. And Q, I don't know what the probability of H is. So let's just say that it's the number B. And then the probability of tails is 1 minus B. And I'm using B here to stand for bias. So I'm going to use the second formulation for computing f of q y, and I'm mainly going to be focused on the what's called the complexity term here. So the complexity is d sub kl q of x double line p of x is the Kullback-Leibler divergence of this. So my memory serves, this is equal to the sum over our possible outcomes. Let me just look it up since I'm not remembering it immediately. One thing that's fun is the way the Q and the P in the book are reversed from the Q and the P in the formula, so I have to make that mental switch. So this is going to be the sum over Q of x, sum over x and x of Q of x times the log of Q of x over P of x. And so this sum over x and x is like the h and the t. So we're going to have an h term and a t term. So we have Q of h log Q of h over P of h plus Q of t log Q of t over h of t. So this will be so Q of H was whatever my bias is. I don't, it's a value, it's a number B. Okay, so then log of B over 0.5 plus 1 minus B log of 1 minus B over 0.5. So this depends on B. But we can now, that's all it depends on is the probability of heads. So we can make a plot of this where we have this quantity is the output, D is the output, and it's function of B, and it will be equal to this. And what this could give us is an intuitive sense of, for instance, how quickly the Kullback-Leibler divergence grows when, as the bias gets further away from 1/2, as the coin becomes less and less fair. So I'm going to see if I can plot that with, I don't think I can plot it with D's and B's in Desmos, but let's try anyway. And if I can't, we'll just switch the variables to F and X for the standard. So D of B is equal to B times log of B divided by 0.5 plus 1 minus B times the log of minus B divided by 0.5. This is what it looks like. It's roughly, no, it's concave up, symmetric about 0.5. Maximum value for this base of logarithm. Looks like it's, you have to take a limit. Looks like it's approaching 0.29, maybe 0.3. What this tells us is this quantity of Kullback-Leibler divergence between these two, which is also called complexity. Then we can look at the accuracy. The accuracy depends on data Y. And for me, I feel like, okay, if I did this and I looked at this and I now know that this quantity looks like this for 2 coins, I can understand intuitively if I have a biased coin, but I think it's fair, the complexity gets higher and higher as the coin moves further and further away, and I can kind of see the shape of how that happens. And so that's something that's helpful to me. And I'm trying to do that with all of these things to come up with some simple concrete calculation I can do that connects to something I feel I understand, so that it's not just a huge pile of symbols. And then I've also noticed in looking at the appendix that there are times where this pops up as a actual calculation in a more relevant context, for instance, where people are like, let's find the complexity of using one distribution to approximate another, or let's calculate something about that. So having done this once, I feel more prepared to do it again. And that is called the Polya principle. It's named after George Polya, who wrote How to Solve It. He said, if there's a problem you don't feel comfortable with, there's a smaller problem that's related that you do feel comfortable with it, and you can solve that one instead as a starting point. In this case, the problem we worked through was like just finding an immediate concrete example to try to latch onto. But that's the whole strategy, is to create things in chunks so that it never becomes totally overwhelming. Okay. Is there anything y'all would like to do that with for next time that's currently in the textbook where you'd like for us to try to go through it in a concrete way and make it more, what's the word? Less abstract, less vague.
Hello, sorry. Can you hear me?
I can hear you, yes.
Yes. Thank you for doing this. Yeah, I was a bit late, so I didn't hear what you said in the beginning, and it's the first time I'm here. So maybe I'm saying things that are redundant with what you've done before. But for me, it was especially chapter 4, which was very unclear how things well kept together somehow. Like there were some jumps in the. It's a while ago that I looked at it, so I would have to look again to be very precise in what I don't understand. Um, but also in this chapter, the three formulations of the free energy, how one goes to another is totally unclear to me. Like how these derivations, how that they actually are the same. That was.
It wasn't clear to me at first either. Actually, last week we
What was
were
unclear, but I guess
so this is like the third or fourth of these sessions we've done, and we're still working through exactly what a structure or format looks like. So I'm just trying to go through things that might be helpful, both in terms of if people have specific questions, I'll do what I can to figure out where the information is or what we can do with it. And then also, as I'm not I have a strong math background, but I don't have a strong background in all of the math in the active inference, and I'm learning active inference. So a lot of times it's like, oh, okay, I read this week, and here's how I tried to understand it. Just sharing things that worked for me or might work for other people. Our goal is to unstick ourselves as much as we can and just have a richer experience with it. The specific thing you're talking about with the proofs of the equivalence of the different types of variational free, or the different calculations of variational free energy, we actually did that last week in detail.
right.
So I can share that link with you, and then
Yeah, that would be very nice.
Testing it from there. Are you on the Discord? I can put it in the Discord, and I think you can.
Is there a Discord?
Yes.
I'm not on a Discord. I am on the Coda.
Okay. I will add it to the Coda then, a link to it on the Coda. And I have my own page, which I need to start using more. for these
Uh,
discussions, and
But I'm not very acquainted with Coda yet, so yes, I'll try to find it and then.
let me see, because yeah, I'll try to find it too. And if you come back next week, I can be sure to have the link ready for you.
Okay, thank you very much. Well, I'm going to check to be certain that I can be there next week. Otherwise, it's the week after, I guess.
Yeah.
Yeah, that should be fine. Next week, I'll try to be there.
Cool. So in the Coda,
Is there a Discord that you said?
yeah, there is a Discord. Let me see if I can drop. I'll drop you an invite via private message in the chat.
Thank you.
Cool. Well, if you don't mind my asking, how do you pronounce your name, friend?
My name is Joris.
Yours.
Joris Grauwels.
Okay, Yoris. Is that? I hope I'm.
Yes, that's fine. Have heard many variants by now, so it's fine. Whatever.
I'll do my best. Yoris. Yeah, so I was actually starting this session by saying I was low on preparation. Like last week, I had all the proofs written out and some exercises we were going to do together, and this week it just didn't happen that way. But if people can let me know specific questions ahead of time, I usually try to prepare something, and if not, we just kind of show up and freestyle it. Because
Okay, great.
anyone have any other thoughts they'd like to share before we close? Okay, well, I'm getting the Discord invite.
I like your shirt.
Oh, thank you.
And thank you for today.
Yeah, thank you all. If we keep coming, we'll keep learning. Yeah, so if anyone is not in the Discord and you would like to be, I'm putting a link in the chat right now. And I hope you all will come again next week. And if you let me know questions in the Discord, I'll try to think about more specific things that we could discuss.
Thank you very much. See you next week then.
Next week.